Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Hello, friends of AI, Earth and Sustainability. I would like to welcome everyone to this seminar series on AI for Earth and Sustainable Science. This seminar series is in this program of AI for Good of the ITU is co-convened by myself, Gustav Kamps, Marcus Reichstein, Joachim Dentla, Maria Piles, and was actually initiated some time ago in the context of the Excellence Network ALICE for the development of AI in Europe. First of all, I would like to thank the attendance to the meeting, all of you. Today we will have two talks, one on remote sensing for marine sciences and the other one on vegetation monitoring with probabilistic deep learning. It is my absolute pleasure to present our speakers today, Devis Tuia from École Polytechnique Fédérale de Lausanne and Nicole Lang from the University of Copenhagen. We will first start with a talk by Devis Tuia, then we will have some questions and answers from the audience, and then continue with Nico's presentation, followed by some questions and answers too. And finally, we have further discussions. Maybe we can continue the conversations, and of course we can rely on the neural network platform to continue those. Let me introduce first Devis Tuia. Devis, first of all, is a good friend of mine, and also, of course, he is a PhD on computational science and earth science in the University of Lausanne in Switzerland. And after passing through the Netherlands, chairing the Geoinformation Science and Remote Sensing Lab there, he's now back to Switzerland. He's actually leading a group of machine learning and computer vision for earth sciences. Devis' research is highly interdisciplinary, as you will see very soon, and very innovative. He has contributed to many subfields to make our planet more sustainable. I would like to welcome Devis, and over to you.
Thank you, Gustav. Thank you very much for the very kind introduction, and good afternoon or good morning, everybody, who decided to attend these two talks. So I'm very excited to hear Nico, and I hope you are very excited to hear what I have to say. So let me share my screen so that I can start with the slides. Oh, that's interesting. Yeah, up. There we go. Can you see it okay? Gustavo, can I have a thumbs up or something? Just to make sure that...
Yes, perfect. Yes.
Yes? Fantastic. Yes. Okay, so today I wanted to give a talk that is quite different from what I usually talk about. And these are projects that have been running in my lab since approximately 1.5 years or 2 years. So it's very new material, and I must admit that it's for many things that I will show today, it's the first time I talk about it. So I'm super excited, and I'm very happy to share all of this with all of you. And basically, this is all about research that we are leading for understanding the oceans, basically, in both directions, so above and underwater. So that's why I chose this title, and I hope you will enjoy the ride and share my excitement at the end of this 45 minutes or so of talk. So basically today we are talking about the SDG number 14, which is it's called Life Below Water. So of course we're talking about above and below today, but That's the closest match I could find. And so studying the water medium is something that is quite new to me, but it's very, very exciting. And as you can see here on the slides, I mean, this goal is very ambitious and have many different targets. And today we're going to focus on 3 sub-targets of the SDG number 14, which have to do with the reduction of marine pollution on one hand, so target number 14.1, and then 14.2 and 14.5 that deal with protecting marine ecosystems and protecting coral reefs. Okay, so these are a little bit the two different flavors this talk will have, but we'll stay on a very marine flavor, and I hope that you will like it. But why studying marine ecosystem from our perspective, so the AI and remote sensing perspective is important? But because the health of the ocean is closely tied to our health, to us all. So as humans, inhabitants of the planet, for a number of reasons. So first of all, I mean, fishes are a very big source of food for many people. So it's estimated that roughly 3 billion people rely on fresh seafood as a main source of protein. So we should really protect all this source of food. And also the food that we eat should not be contaminated with microplastics. And this will be a big part of the talk today. It's like how to map and monitor plastics before they disaggregate into microplastics and then enter the food chain. And then there is also all the aspects related to biodiversity, because coral reefs are a tiny little part of our oceans. So it's like 0.1%, so it's really not much, but they host a lot of the marine life that is in the ocean. So it's 25% of all the marine life. So you can just imagine that if corals die, well, this is an entire marine ecosystem that will pay for the consequences of it. So it's very important to protect them. And not only protect them for the marine biodiversity, but also for our own sake, because the coral reef protects the coastlines, they break the waves, and they make that our coastline is less affected by oceanic patterns, which support protection of activities along the coast, and also give us a lot of revenue in terms of tourism and the like. So long story short, I mean, coastal ecosystems are super important, and this is why we're talking about that today. Because in 50 years, we have lost half of the corals already. And as you can see here in this image on the left, which is a typical bleached coral reef, we are seeing more and more of this due to, I will show you later why, but it's mostly related to what the increase in temperature in water, human activities, and the like. And on the other side, the increase of plastic in the oceans is very worrying, at least for me, because we are throwing more and more plastic in the ocean, and this is starting to seriously affect the health of life, especially fishes and birds. So basically, I don't know, I'm a diver, so I really like to think of our ocean like what we see in the image on the left, so a very healthy and biodiverse ecosystem, rather than what we see on the right. And these two pictures are not so far from each other spatially, and so I think we need to really fight and struggle to keep it as we can see it on the left, and avoid having the degradation of all these ecosystems. Okay, so I promised you to talk about life above and underwater. So I'm going to talk about both aspects in sequence. So we'll first talk about the different researches that we are leading above waters, thanks to remote sensing, to talk about floating plastics. And then in the second part, we'll talk about coral reefs and see how we can use remote sensing to monitor better the health of the corals. I hope that's okay for everybody. Well, I mean, I hope it is. Otherwise, Okay, so part one, let's talk about what happens above the water, and subtitle is Detecting Marine Litter from Space. So we're going to talk about that for maybe a quarter of an hour, and to show you how we are tackling this problem here at my lab, ECO in EPFL in Sion, Switzerland. So as I was hinting at in the introduction, marine litter is a big problem. So the plastics that finish in the ocean, they decompose in microplastics, and these microplastics, then they are a really direct danger to the animals. Okay, they have been found everywhere, in the Antarctic, in the sediments, also in human stool. So they are already in the food system, and we should like strive to avoid this to become worse. I mean, you see some numbers here on the left. So we are talking about hundreds of million tons already in the system, and like roughly 10% of this being always added to the system every year. And this is like, for me, that's unacceptable, and we need to do something. But I mean, if you look at projections of how the thing is going, we can see that, you know, all the dashed line is basically projection on how this is going in terms of quantity of plastic entering the marine systems. But you can see that this is growing exponentially. Okay, if you look at the black line, this is the projection of what is going to happen. And okay, production of plastic is going up and up and up and up. And for the time being, so if you look here where the red circle is, basically all of it is discarded and not recycled. So we are doing a lot of efforts as a you know, global population to make this better, and we see some very positive impulses. As you can see here in the green, like the projections are that we are recycling more and more, and this will help avoiding that most of the plastic produces finishes in the ocean. But I mean, if you look at the red line, in the end, a lot of plastic is not recycled, so a lot of plastic will keep entering the systems. So this means that in a way, we need to be ready to make our part and be able to avoid this entering the food chain. So for this, you know, technology is being developed and implemented, but as a first step, people have been trying to understand how the plastic was congregating in the marine ecosystem. And, you know, thanks to the ocean currents and the like plastic tends to aggregate in regions that are very well localized in space, as you can see here in the middle picture. And there have been quite a lot of efforts to collect this plastic. So if you can see, this is what we call a windrow, which is basically an aggregation of plastic. And if collection action can locate these windrows, they can then, you know, remove the plastic from the system, and it will then avoid to enter the food chain. And there are several companies that are active in this. For example, I'm sure you have heard of the ocean cleanup, and basically these companies are doing what they can. But for them to be very efficient in these collection actions, I mean, in a way, they need to know where this plastic is. Okay, and to know where the plastic is, well, our bet is that in a way we can use remote sensing to actually locate this big congregation of plastics, hopefully more close to the coast, so before the plastics enter a very large system that is the ocean, and then we can kind of guide and help these collection actions to make what they do at best, which is collecting and recycling. So by using remote sensing, we can maybe support this type of actions, and then provide a service that would be very useful for make these campaigns efficient. So basically, we are looking now at a couple of satellite sensors that could be used in this respect, which are, as you can see here in the black part of the slide, the sensor called Sentinel-2 or PlanetScope. And the basic question we're asking ourselves in how well we can detect first, then map at scale, and eventually, when we get there, monitor marine litter from satellite data. So we'll not talk about monitoring now, because this will imply integrating, you know, oceanographic current data, but we are now busy with the mapping part that I want to talk about today. So I was talking about Sentinel-2 and PlanetScope. So there are two very different type of satellite sensors. I mean, if you are from the field of remote sensing, I'm sure you know everything about it, but if you're not, just you can see here first images of the satellite and the different specs. So basically, Sentinel-2, it's a mission with a constellation of 2 satellites for the moment, which is taking images in the optical range, so red, green, blue, and near infrared bands mostly, and at a 10-meter pixel size resolution. And the satellites, they are 2 that turn around the Earth, which means that every 5 days, let's say, we have an image of the same place. This is good. but then the big question is it 10 meters enough to detect plastic at sea? We will see. And then on the other end of the spectrum, pun not intended, on the other end of the spectrum, we have the doves of PlanetScope, which is microsatellites. So we have 150, 160 on them, and they give us a better spatial resolution. And we're talking about 3-meter pixel size. They come back every day because there is a lot of these satellites. flying. But we have less spectral bands, so we have red, green, blue, and one infrared band. Well, now they have new products, so there are sensors that are better. But maybe the big pushback is that it's commercial, so yeah, you will have to open your wallet to get the images most of the time, and so this is maybe difficult for a company or an NGO that doesn't have a super big means to use something like that. Anyway, I think the two sensors are very useful in their own objectives, and they're very complementary. Okay, but if we look at the different image they provide, I give you here two images, one per each sensors, focusing on the same area. I mean, the red square here corresponds to the footprint acquired by the planet, so you can see more or less what you can see on this type of images. So of course you see the difference in the spatial resolution, but the Sentinel has the advantage of being free and to have this continuity. Okay, so basically, how can we? So we start to observe satellite images thanks to these sensors. Let's focus on Sentinel now, but same applies also on Planet. I mean, the first thing we can notice is that by using RGB images, so the typical images as you could take with your phone, just from space, but you don't see much about the plastic. So you see some of it, but most of it remains hidden to the human eye. And this is why recent researchers have been focusing more in developing indices that exploit the near infrared, mostly because the algae is strongly reflective in the near infrared, and having this as a proxy, we try to map the plastic thanks to the algae that we can observe. So there are these indices, maybe the NDVI, it's one of the most common. But even when we use these indices, as you can see in the graph on the right, I mean, it's complicated to discriminate type of plastics. There is no really linear distinctions between plastic and non-plastic, and also not between the different types of plastic. So I think we need something a little bit more advanced, and this is like kind of a motivation for us to build something that is AI-based instead of working directly with indices. There is also a second problem, is that the indices themselves, they are sensitive to things like the coastline, for example, or the sea spray. As you can see here in the floating debris index, the coastline it's very, very active, so it can be mistaken by plastic debris. Okay, it could be simple to remove that if you have a coastal mask, but then there are other problems like the clouds, for example. Clouds, like the big enemy of optical remote sensing. So clouds, we start detecting clouds as plastic, and we don't want that. And then human objects that are also floating in a way, but we are not interested by this object, like ships, for example. So a ship is a floating object, but it's not the type of object we want to detect because we don't want to collect it, basically. So, we need a classifier that could take advantage of all this data, but then will not be fooled by all these type of confounded factors. And that's where we started to look into machine learning based approach. And for example, deep learning neural networks, it's something that we are now experimenting with and exploring to see what will be the best design to be able to map the plastic debris at sea with a high accuracy and with a method that is, let's say, as simple as possible. So here is, as you can see in this slide, it's a bit of the, like the classic recipe for deep learning image segmentation. So you start with some images, as you can see here on the left. So it can be the Sentinel-2 bands, it can be the indices, the NDVI or the FDI that we extract from it. And then we have a model that we learn from this data and then end up predicting our debris that you can see as a probability map. So as you can see here, everything that is in reddish colors is considered as plastic here in the sea. And of course, to train this, we need, of course, the image data, but this fortunately we do have, and we can, we can select some images and location with respect of plastic outwash events that we are aware of, and then create some kind of learning data to train the deep learning model. Okay, this deep learning model, what does it look like? For the moment, we have been experimenting with traditional semantic segmentation models. So it can be like a unit, which is probably the most successful semantic segmentation model around, and then some some improvement on it, like the UNet++ that basically adds a lot of dense connection between layers. But it comes from a similar philosophy, let's say. And in a way, we are fixing the deep segmentation model part with these two models, and we try to experiment what is the best setup for having our marine debris classification. You will see in a second. So the thing that we did is that we started by creating a data set to learn from, because otherwise, I mean, we need example of what the marine debris look like in order to be able to detect them. So we took a number of images by screening the news and seeing where there were these floating object events, and we could find a number of events that you can see in blue in the blue map. And this was the work of Jamila Mifdal and Mark Rusfulm, who is now in my team. And they came up with this data set of images taken from the Sentinel Hub and then hand annotated, as you can see here. So they were annotating the plastic they could see by screening the Sentinel-2 tiles, and also with using the indices and making sure that the ground truth is correct. And then on the side, I just come back on a slide for a second, we took the existing data set that is the one from Kikaki and colleagues, where they also had Sentinel-2 tiles with plastic events, and they were even classifying the type of plastic it was, but we just took it as a plastic, non-plastic from the time being. And then with this data set, we started experimenting. And at some point, we realized that, we had this problem, like the ships are very difficult to detect. And then we decided to actually add a third data set that you can see here that is called the S2 ships data set. That it's a data set that it was basically created for something completely different, that it was ship detection. But this data set exists and it gives us examples of what a ship looks like at sea. So, like in this example here, you can see some ships in the open sea. Sometimes they are on harbors and so on. But this we can use, you can enter in the data set because we give data as like hard negatives, like in a way that we know that this example must be classified as negative. And if the model starts to classify this example as plastic, but there is a problem. So let's say that we are taking a little bit more of a data-centric approach where we try to optimize data to solve the problem with a fixed model, rather than try to trick the model with a fixed data set. And in a way, I will now give you a couple of results without going too much into the details of the nitty-gritty details, but we have observed a couple of things that are very interesting. So on one hand, we see that, okay, the deep learning model seems to outperform like traditional machine learning. And here, I'm not telling you anything that you didn't know before. I mean, this has been shown a number of times that when you go on a neural network with a lot more parameters and flexibility, maybe you train on much more data and you get with a model that performs better. But still, I mean, this is not always the case. Like you see here in the second example, the Durban one, you can see that the random forest is doing a fantastic job. It's doing actually better than the neural network. But for me, the big take home here is that, okay, deep learning versus non-deep learning, but that's for me, it's a kind of a sterile discussion. For me, the important thing is that whatever we do, when we use a data set that is crafted for the task at hand, whatever model you use, everything gets boosted. And having this type of philosophy on try to craft a data set that it's really important to solve the problem is what really makes the difference. And here you see, okay, we have a little bit of advantage for UNet++, but that's irrelevant. I mean, the important thing is that we have a very significant jump just by crafting a data set that makes sense for this task at hand. So, I mean, despite the story of plastic, which of course is the important story today, I also wanted to pass this message is that, think about your data as well. Don't think only about your models. And okay, so here I have a couple of prediction examples. So we have here in the first column is just an image of the region. Here you have one of these floating object indices. And in the truth column, it's actually the data that have been hand annotated by my colleagues with a lot of energy and persistence. And then you have the results of 3 different models. So we have the unit with the enhanced datasets. We have the unit with the original data sets of Mifdal and Rusfulm so using only that without the data set of Kikaki and the S2 ships data set. And finally, the random forest trained only on the Kikaki dataset, because that's what we were using as comparison also before. So you can see that actually, I mean, it's always a mixture of all these different components to have a good prediction. But basically, using the enhanced dataset gives you a prediction that in the end it's taking the best of both worlds. And we also have an Earth Engine app if you want to just go around and see where the plastic are. Then I guess it's complicated to copy it right now, but maybe you can take a picture of my screen and look it up afterwards. And especially Mark will be super happy if you all go and check it out. Okay, good. And finally, before moving to the second part, because time is running very fast, but I still have time, it's fine. We also tried to study how this could work by the conjunction of the two satellites, because so far we've been talking only about Sentinel-2. But you remember Sentinel-2 has a revisit cycle of roughly 5 days. So it means that you see the plastic today and then you see the plastic almost in a week, no? But if you want to really do some monitoring, like following the plastic and or just having a more detailed view of what's going on, you could imagine of switching to planet images, for example. And in this case, we tried to see if it was possible to take our model learned on Sentinel, relearning it only just for bands, and then applying it on PlanetScope images with a slightly degraded resolution, just that the jump is not too big. And then we realized that the thing it's working not so bad. And we took as a case study the Plastic Litter Project 2022, run by Kostas Topouzelis and colleagues in Greece. And every year they deploy targets in the sea. So it's I don't know, a raft made of plastic or things like that, and they leave it out for 1, 2, 3 months, and then they take all the images acquired by different satellites, Sentinel or Planet, and they make them available to the community. And the cool thing here is that we have been working on this data, and actually the model is able to detect the plastic in the Planet image, even if trained on the Sentinel image. It still makes a decent job in detecting the plastic also in the higher resolution scenes, which is very cool. And moreover, at the beginning, we were a little bit concerned because, I mean, you can see here in the image, you have one very bright target, and then you have 2 others that are not so bright. And we were like, oh my God, we are detecting only one. This is a pity. But yesterday, Kostas Topouzelis was visiting us here at EPFL, and we were just talking about it. And apparently, the top targets are wood, and the bottom one is plastic. So basically, the model is actually doing a very good job because it's detecting only the plastic one and not the wooden one. I mean, to be continued, but in a way, this is kind of a positive signal that the model is using something more than just a very simple visual cue. But I mean, we will see how this unrolls in the future. Voila. So let me have just a sip of water. And in a normal talk, this is where I will ask if there are questions, but please, please write your questions in wherever you are in the neural network, and then I'll try to answer them afterwards. So let me move to the second part, which is about going underwater this time. So far we have been doing somehow a traditional remote sensing study where we were taking images from satellite, from above, and then try to cartography the plastic floating at sea. This time we take another perspective that honestly for me is less what I'm used to, but it's a project that I'm really having a lot of pleasure running here with my colleagues at EPFL, and we are working underwater to map and monitor coral reefs at scale. So basically, what is going on? So just a little recall from the introduction. You remember that I told you that we have lost roughly half of the corals in the oceans. Okay, and this is I mean, very problematic for all the reasons I stated before. But why is this happening? And it is basically happening because first of all, I mean, climate change. So the water temperature increases, which makes that corals are under stress. And when they are under stress, they expulse the algae that they live in symbiosis with, which makes them bleach, so they become white. And that's after some time they just die. And this is done because of the temperature increase, but also because of the pollution of the water and the tourism, people stepping on the coral or things like that. So corals, in a way, they are under threat and they deserve to be preserved because, they host a quarter of marine life. They protect us from all kind of wave patterns that would erode the coastline and so on and so forth. Okay, so why have we decided to do that the way we are doing it? So we are basically studying this in the Red Sea. And this is not just because it's the closest coral reef that we have with respect to Switzerland, because, okay, in Switzerland, we do not have coral reefs. Actually, we do not have sea at all. But it's because some colleagues of mine have been working with local colleagues around the Red Sea, and they discovered something that is very, very exciting. Is that the corals in the Red Sea resist to the heat much more than corals everywhere else. So if corals in, let's say, the Great Barrier Reef will bleach with an increase of temperature of 1, well, in the Red Sea, they can sustain increases of temperature of 3 or even 4. So they kind of are like, we call them super corals sometimes, because they're very strong to temperature variations. And, this is as my colleague Anders Maybon always says, it's kind of a message of hope, no? That there is hope in the Red Sea to have a last sanctuary of where corals will remain if we don't manage to protect them everywhere else. And the thing that we really need to understand is why this is happening. So why corals are so much more resistant in the Red Sea. We start to have an idea of the why. But besides the purely, fundamental science question of why they are more resistant, we also somehow need to map and monitor and report because we need to follow how the evolution of the corals is going, both in the Red Sea and everywhere else, because we need this as a matter of pressure for government, as a way of documenting what's going on. And so it's really important in a way to have a first-person view of what is going on in below the surface of the water. And it's something where, it's not so simple to do it with satellite remote sensing. There are colleagues who are taking that way, like, the Allen Coral Atlas, for example. It's a super example of how we can use hyperspectral technology to map corals, and they're really making some giant leap. In our case, we thought, okay, let's try to get very close to the corals so that we can map them in a way that it's really like very visual for people, and also it allows us to go really into the morphology of the coral and try to understand why some are resistant and some are not. So this is not something that we invented. I mean, making photogrammetry underwater is something that exists since a while. Like in the example here of from this paper in 2015. So it has already been done in a way to have a diver with a camera taking some images and then trying to make a 3D reconstruction of the reef, for example, using technology like structure from motion. And this is fine. But the story is that the photogrammetrical methods, they are super precise and work very, very well. But, the traditional way of doing photogrammetry, it's maybe not so good at scaling up. While, for example, in the study of 2015, to making a 28 meters by 6 reef part, it was a 1 hour of 3D reconstruction using Photoscan, which is a proprietary software, and then several hours of manual work to extract the information, the typology of corals, if they're bleached, if they're not. So there was a lot of manual work typically in a GIS software to make sure that we could extract the information that we wanted from the 3D model. And this, gave us this envy to make this in a little bit more friendly and open way. On the other end of the spectrum, very recently, there are papers that are doing fantastic jobs at mapping the different benthic categories of the coral, but they use setups that are very complicated. Like in this paper, they're using what we call a hyperdiver, which is a hyperspectral camera. So it's a camera with 200 spectral bands, with which they film the coral reef. And thanks to this camera, they can do this fantastic characterization of corals. So yes, this is great, but it's difficult to scale it up globally because, this camera is extremely expensive. So it's a setup that not everybody can have in their own pocket. So we try to, take our stand with respect of these two setups that are, each one extreme in their own way. And we took the bet to go with affordable setups. And since last year, we have started to really research way of doing remote sensing, but pretty close this time. So with cameras, but with setups that are very simple. Okay, so we are basically using GoPro cameras that you can buy in your favorite electronics store, and we have been creating these very simple setups when we have a diver, so a very happy graduate student in my lab, Jonathan Souther, you can see in both images, that is basically diving with a pole with these two cameras, or in our new setup, with these 6 cameras, and it's basically filming the reef. And this is cool for a number of reasons. So first, it's scalable. If you go for your holidays, you maybe have a GoPro with you, so you can acquire data for us. Second, if a camera breaks, you haven't lost, I don't know, $50,000, but you have lost something that maybe you can afford to replace. And third, we can also train local communities. We can, we can provide this type of cameras, and we can, in a way, empower them to take their own data, so that we don't have to go every time to all the reefs in the world. So I think it's a project that joins a lot of good points. That is the scalability, the training, and also the feeling of doing something very important. Okay, but now apart from the technical setup that we use for acquiring the data, basically we have created this deep learning model that, given a video acquired by a single camera, so for the moment we are using on single camera setups, even though we have multiple, but we can use the different cameras to acquire different parts of the reef, or maybe at some point in the future we'll also consider working in stereo mode, but for the moment we are not. What we are doing is that we have a single camera that is taking a video. So it's in video mode, the diver is diving, and we get to our video, and then we basically analyze all the frames with a model that is doing 2 things. So first of all, it's doing it's doing depth and pose estimation. So it's basically making a depth map from every frame. And the second model is doing semantic segmentation. So for each pixel, it's trying to tell us if it's an healthy coral, a bleached coral, a massive coral, if it's too far to be classified, if it's sand, if it's rocks, and so on. Of course, the model below, the semantic segmentation one, needs annotation. So you can see here our wonderful colleague Gabi, who is annotating a frame of the image with different examples of the different types of corals, and we use this for learning. But the tasks above, so the depth estimation, is completely unsupervised. And I will show you in a second how it works. The story is that we have this model that, when we have it trained, it needs to 3D reconstruct an entire reef, let's say 100 meters or more. I mean, it depends on your diving time, but it needs to do it in basically plain video time. So the thing that we want to reach is, it's 20, 25 frames per second. It would be something super. And last year we tested it in 3 places: Israel, Jordan, and Djibouti. And now we're processing all the data, and we're having a lot of exciting results that I want to share with you for the very first time now. So first we have our model that does pose and depth estimation. So what happens is that we take basically 2 subsequent frames at the time, and we try to make a depth prediction for each one of them. So in every one of these images, whatever is more yellowish is something that is close, and whatever that is very dark blue is far away. And to train this, we use basically the fact that these 2 frames are one after the other. So if we can predict the pose, which is the camera and position and orientation for the 2 frames, we can basically predict the depth for frame A, project it in the location of frame B, and superpose the 2 predictions, and they need to be the same because the reef has not moved, we have moved. So by playing this trick, we can do stereo because you're basically simulating the fact that you have 2 eyes by closing one and then closing the other. And this helps us to have a loss that we can reproject, and helps us learning the depth map. The other model, the semantic segmentation, it's a kind of a last generation UNet, so it's the same model as before, but with an encoder that is a little bit more recent than the one that we were using before. It's the ResNext. And thanks to all the effort of our annotators that are still annotating, we get to interesting accuracies of 80% plus, which actually allows us to have something that we can basically trust and also use to do the 3D reconstruction. Because when we do the 3D reconstruction, meaning that we take pixels of every frame and we project them in the 3D model, we are very careful not to project everything that is predicted as a fish, for example, or a diver. No, because these are not part of the reef. These are elements that are just transient. And so if something is classified as a human, we will not put the human in the 3D model. So we just ignore those pixels, hoping that the human will, get out fast enough that other pixels later on in the video will be able to be projected at that specific location. So it's a bit of a multitask model where the segmentation helps the depth estimation, and having the depth estimation also helps us predicting what we are looking. For example, everything that is blue here is called background. It's basically too far to be classified. And we can classify this very well thanks to the depth estimation. So the two models basically talk to each other because they have a shared first part. And yeah, that's it. I just wanted to show you a little bit what it looks like. So this is a video that we prepared that shows an actual dive that we made. If I remember well, this was in Israel. And you're actually, you are being the eyes of Jonathan through his GoPro camera, and he's following a line that you can see here in the middle. So it's classified in green in the semantic segmentation. So here you see the line, and you see all the types of corals, and in red you see the fishes, and the different shades of orange and pink are different types of corals that the model is classifying basically in video time. And this is okay. It's not embedded in the camera, but it works in 18 frames per second. So it's basically video time. And here you see the depth estimation here on the top right figure, where everything that is yellow is close and everything that is blue is far. And at the bottom, one frame at the time, you see the 3D reconstruction being generated. Okay, so every time the model has processed one frame, it decides which pixels are to be projected in the 3D model. And this pixel come to nourish the 3D model that is being created as long as the video goes. And this is like, of course, it's for sure less precise than a structure from motion system, but it is very, very fast. Like it's predicting, again, in video time. So it's being predicted as you are looking at the video now. Of course, this is a video that I prepared in advance, but I mean, the model is running and creating the 3D model. And this, I think, is the advantage that permits the model to scale up to a scale that with current photogrammetry methods is maybe not yet possible. But okay, so we got to results that look like this. So we are looking at reefs that are more or less 100 meters long. And, you have the 3D reconstructed reef, the semantic segmentation result, and then the depth mapped, so considered as the maximum depth predicted by the different frames where a pixel is seen, and then we can do all kind of mapping efforts. It is like seeing which type of corals you are observing, what are the percentages, and so on. And now, by coming back to the same places in the future, then we will be able to monitor how the coral is doing and evolving in time. I mean, or at least this is what we hope for the future. Okay, so this is more or less what I wanted to tell you today, and I hope it was a good ride, and it was also a bit fun and good to see and beautiful, but also inspiring in terms of sciences. I honestly I was not working in the water domain until a few years ago, but now it's getting really a lot of passion. Also probably because I love the oceans, but it's also because I think it's one of the big challenges of our time to protect them. So just if you need to remember something from this talk, just remember so that the oceans are very important for the survival of ecosystems like marine and not, including us, and then also that with modern AI tools we can make our parts to at least observe, monitor, and protect. And this cannot just be done by a computer scientist. We work with interdisciplinary team. We work with the marine biologists, with geneticists, and we really try to get to the bottom of this. I mean, not a joke that I wasn't prepared. And that's it. So thank you very much. I also wanted to thank all the people that makes this possible. Here on the top left, you see Guilhem. He is the guy who's making all these beautiful pictures of corals that you have seen. Here in the middle is Jonathan, who is making the dives together with Guilhem and creates all these films with corals going on. And also, you know, Anders, Mark, Dilge, and all the other students, Emanuele, and Susha, and Julia, and Laura. So thank you for your attention. And also thanks for the people we work with, the Translational Literacy Center, the Ocean Cleanup, and the Swiss Data Science Center, who supports us all the time. Thank you so much.
Thanks so much, Devis, for this great talk. It was really a pleasure to have you here and to see these new things that you have to show us, and a bit different to what I was really accustomed to see from you and your lab. I'm pretty sure that there are like a lot of questions and doubts and curiosities in the chat. Maybe while people is kind of warming up, maybe I can question something.
Sure.
Yeah, well, my first curiosity is about, okay, in the first part you showed us like a complete pipeline, let's say for the plastic detection and debris and everything, and heavily relying on deep learning architectures, well, more or less, right? I mean, even though the point was the data, right, rather than the models that I can call on that. But I was a bit curious about if you guys took a look at what the models learn actually, right? So in a way of, I don't know, maybe applying some sort of explainable AI techniques or something like that, if it's paying more attention to some particular bands, to some particular resolutions or things like that, I don't know.
So for the moment, we have been looking a bit to the occlusion sensitivity analysis. So to see if the model was focusing actually on the plastic, we're predicting the plastic, because at the beginning we were casting it as like an image classification problem. We were sliding around, and so of course when we use a lot of data, the XAI analysis points to the plastic, no problem. But then now Mark Rusfurm, so my colleague who is leading this project, is we're working on like scenarios when we have very little data, because when we move geographically, the sea conditions are different, but also the types of plastic are different. So we're focusing on models that are more agile. So for example, based on meta learning or things like that. And even when we use just a handful of samples for training, so we have gone down to as little as like 5 examples from one scene to fine-tune a model and detect the plastic, and it's still detecting the right thing and highlighting the right regions. So this is like, for me, very, very encouraging. For the bands, the truth is that we don't have a lot of bands to play with, to be honest. And I was talking with Kostas Topouzelis yesterday, and the dream would be the hyperspectral sensor, that where we really can cover the sphere bands where we know that the plastic is very reflective. But for the moment, we don't have much to work with in that direction.
Got it. Thanks. We have a question here in the chat by Sunajana Ghosh. I think that is more concerned about the potential clustering algorithm, and is suggesting, do you think something like deep level sets might be useful for the plastic detection problem?
Deep level sets. So okay,
yes.
So this is some kind, some kind of segmentation, like a watershed, no?
Yes, probably.
Yes, but you still have the problem of finding the right seeds to start the growing. So I think it's not impossible. We could take the highest probability detection and let it grow with respect to what the image is looking at. So why not? I mean, it's a very good idea.
Yeah, actually, that was one of the things that I was thinking. I mean, you put a lot of emphasis on labeling, right, and tackling the problems in supervised way. But we are now aware of many different methods, right? That like mostly based on self-supervised learning, or even, I don't know, all style methods on change detection and anomaly detection that are running unsupervised. I don't know if you explore those, or they are completely out of the scene because they don't work with such a limited data and dimensionality. I don't know.
Definitely. I mean, I think this is for me, it's still a very open area of research. Also, all these students I was showing in the last slide, they were like looking at self-supervised learning and active learning to get more example and so on and so forth. And it's true that, I mean, the enemy in all this is the extreme diversity of what we see in the images. I mean, the ocean is not just water. The ocean is water and waves and all kind of, clouds. And there is a lot of confounding factor. The sun glint, I mean, also, even when there is nothing particular going on, depending on the sun glint, you can have the models going completely crazy. So I think that there is a part of it that working with these like small and agile models that can adapt very quickly to specific situation is the way to go. But I still need to, be sure about it.
Yep. We have an amazing question, I think, a more general one, not that technical, by Hanneke Lackbelt. Says that how do you envision how your work can be used by governments and policymakers? Wow, that's a challenging one. But I mean, we aim to actually impact society. We should kind of think of our, how to translate that into actions and policy making, right? A second part of the question says something like, is our current marine policy ready for outputs from your models? Or, okay. I mean, is this are the products like, ready to be used or to deployed, or I don't know. What's your feeling, right? What's your feeling? What's missing? I mean, how far are we from this actual?
It's difficult.
Yes, it is.
I think we are still at the state of prototypes that are going better and better. We are collaborating, for example, with the Ocean Cleanup, and so it's a company that it's interested in what we're doing because they are out there collecting the plastic. So in a way, with a bit of luck, we can also have this kind of interaction with them where we can prove that this is actually useful. For the moment, we have detections, they look okay, but this is not actually useful. Like if I give them today the information where the plastic is, I mean, will they get there on time or not? Because of course currents move, plastic will move, and so on and so forth. So we have a lot to do to make sure that that the products are good enough for action. It's baby steps. So, but I think we're doing it in the right way. We're not doing it just closed in our bubble, but we're trying to reach out. Also in the Coral project, we really work with scientists from the different countries of the Red Sea and try to empower them so that they can take the data themselves. And this makes everything, first, the countries own it. And secondly, we can really scale to the entire Red Sea. Like alone, we could never do that. And I think this is a good message. And I mean, we will see. Will one day this be used for real policy making? I don't have the crystal ball, but I hope it.
Yes, I also love the way you put it. Like, I mean, the interdisciplinarity, right? The role of collaborating and working with many different teams, with different backgrounds, etc. I think this makes these two projects very exciting. I think. I don't know. I would like to learn more about how do you manage. I mean, I guess that you have to learn different languages, right, and to understand each other. And,
oh my God, this is a question for Anders.
And the second twist on that question would be something like, are you actually incorporating that kind of interdisciplinarity or domain knowledge in your algorithm somehow? Or...
Okay. So question one, this is really a question for Anders, who is running the Coral project. But we really think of it of a project between science and diplomacy, we call it. And we have like the Swiss Office of Foreign Affairs. They help us a lot to get in touch with local governments to make sure that they know that we're coming, what we're doing, and why this is useful. So we're really integrating local people from the start. And also every time we go diving, there are scientists from the place and also now from other countries that come with us, and we define the procedures together. And it's very nice, honestly. And most people speak very good English. When we go to Djibouti, they speak French, so it's even easier for me. And so, I mean, there is a part of it that is very exciting, because it's not just deep learning, but it's deep learning together with local people, with biologists that we're having so interesting conversations, and little by little, I even start to understand them. And the geneticists, you know, they take samples and they analyze them on the boat when we come out of the water. So, I mean, there is a full system of people working, and we are just a part of it. And for the second question, so if we integrate this local knowledge, for the moment, no, to be honest. And now we have a student, Julia Veltri. She's working on with people from Ghana on the Ghana example for plastic to understand where are the sources, where does the plastic come from, and then we try to integrate that into like flow models and things like that. But it's not exploratory for the time.
That's a really good point. Actually, that question popped to my mind in both projects, right? Because in one case, or maybe in both cases, you should kind of integrate some kind of dynamics, right? Like plastic moves, or maybe circulation models or something like that. But even at that very broader scale, maybe they should be kind of useful, at least to pre-locate where the plastic is. On the second one, maybe thinking of acidification and there are some products out there. I don't know. So that was my main motivation. I think that we don't have any further question actually in the chat. Probably, you know,
there is one.
There is one. Okay, cool. Yes, Catherine Kiranaki is asking, are you also using robots to assist you? Wow, that's exciting.
Cool. For the moment, we are working with humans in the water, and it's. I mean, why not? It will be very interesting to, you know, try to think about robotic assistance setups. Then there is always this question that the more it gets complicated, the less we can scale it. So it's definitely something that would be super nice to do. And I mean, let's get in touch to talk about it. For the time being, we are passionate divers, so we like to be in the water, to be honest. But yeah, I mean, why not?
Fantastic, Devis. I think that we're ready to go. Maybe you can stay there. We can now move to Nico's presentation, but still we will have some time afterwards to continue the conversation if time allows. Thanks very much for being here with us.
Thanks. Bye.
Yes, and now I would like to introduce our second speaker today. Nico is a researcher at the University of Copenhagen, associated to the Pioneer Center on AI. In particular, he has been working on deep learning approaches to monitor urban trees from street level images, which is a very impactful application in its own. Already in his PhD studies, he developed an approach to compute a high resolution canopy height model of the entire Earth by fusing optical satellite data, the high resolution, and also a spaceborne LiDAR. His current research interests include quantifying the uncertainty associated to such estimations, and also working on, related machine learning problems involving imbalanced data, and of course dealing with uncertainty in the wild. Thanks for coming and for speaking in our seminar series, Nico. The floor is yours.
All right. Thanks a lot for the nice introduction, Gustavo, and thanks, Devis, for the super interesting talk. So let me share my screen. So I hope you can see the slides now.
Yes, perfect.
Okay, thanks for the confirmation. All right. So the work that I'm presenting today was actually done during my PhD at ETH Zurich, before I moved here to Copenhagen to do a postdoc at the University of Copenhagen. My talk is titled Global Vegetation Monitoring with Probabilistic Deep Learning. And before we dive into some technical details, I would like to explain quickly why is it so important to monitor vegetation globally. As you might know, forests provide very important ecosystem services. And the two most important ones, I would say, are that they provide livelihood for about 80% of terrestrial species. And they also have the ability to absorb and store carbon from the atmosphere in the form of biomass. So they have the ability to regulate the climate from local to global scales. And in the context of the Sustainable Development Goals, the United Nations have come up with the so-called Global Forest Goals, where they, for instance, would like to see an increase of the forest area by 3% until 2030, and they want to maintain and enhance the forest carbon stocks. So these are very ambitious goals, and they are related to two global challenges. So first of all, we want to mitigate climate change, and we also want to avoid biodiversity collapse. Now, how can we monitor these goals? To be able to make sustainable progress, we need data that is global, high resolution, and fine-grained. And with fine-grained, I mean continuous vegetation, characteristics that allow us to quantify, for instance, carbon. So we need to go beyond binary forest, non-forest maps. And one key indicator to map, for instance, carbon stocks and biomass is vegetation canopy height. And today it will all be about mapping canopy height. So unfortunately, it can be very challenging to collect data about canopy height in the field. So imagine climbing every tree and measuring its height. That is an approach that, for obvious reason, does not scale to large areas. And how can we measure vegetation height today? So luckily, there is a bunch of remote sensing technologies that can support this task. However, there's no single sensor that can provide exactly the data that we need. There's always a trade-off between the suitability to directly measure vegetation structure and the scalability of this sensor in terms of coverage and temporal revisit time. For instance, we have airborne LiDAR or airborne photogrammetry, which provides very high quality data to almost directly measure vegetation structure and height, but these sensors do not scale to very large regions, and it's quite expensive to run these measurement campaigns. Then we have spaceborne LiDAR, where we have laser scanning sensors in space. They allow to map much larger regions, but usually provide lower resolution data or even sparse data. And on top of that, the data might be much more noisy compared to airborne data. And finally, we have optical satellite images, like we have heard from Devis already. This data provides global coverage, high resolution, but they are actually not really designed to measure canopy height or vegetation structure. So we should actually ask a little bit a different question. Instead of how can we measure vegetation height, we can ask how can we estimate vegetation height from these type of data. And that's where deep learning or data-driven approaches come into the game, where we would like to exploit all these different data sources and would also like to overcome some lack of understanding how, for instance, optical satellite images correlate with vegetation height. So today's talk is structured into 3 parts that are tightly connected and built on top of each other. So first of all, I will start talking about how we can map canopy height from Sentinel-2 optical images. Then I will talk about canopy height estimation with spaceborne JEDI LiDAR data. And then the third part will be about fusing these 2 data sources at a global scale. So let's start with the first part, which led to a paper that we published in Remote Sensing of Environment. Here is a quick overview of Sentinel-2 images and the sensor. So Devis already talked about that. It's a multispectral sensor, and it provides 4 bands with a 10-meter resolution. And it gives us a global coverage and a new image about every 3 to 5 days, which is a great source of data, even in frequently cloudy regions, like in the tropics, for instance. So when we talked to some remote sensing experts, and we told them that we would like to map canopy height from these optical images, they usually said that this is a rather impossible task and that we will most likely fail to do this. So the main problem is that we do not really understand how to construct predictive features from the optical images. And one way of overcoming this lack of understanding is to simply learn these features from reference data, so in a supervised way. And we approach this by learning or training a convolutional neural network that can extract textural and spectral features that ultimately are predictive to regress canopy height for every 10 by 10 meter pixel of such a Sentinel-2 image. And we do this by optimizing a loss function. So here we simply use the mean squared error. So we minimize the estimated canopy height, like the squared error between the estimated canopy height and the reference canopy height at every pixel. So to do this, we need reference data, and we started with data from 2 countries. One is Gabon, a tropical country in Africa, and also data from our colleagues in Switzerland. And we run some ablation studies using this data to understand, or to try to understand a bit better, which characteristics of the data and our approach have an impact on the performance. So in this table, you see the mean absolute error. So lower means better. And the first thing we analyzed was different input band combinations. So we remember that the Sentinel-2 images provide 12 bands. 4 of them have a 10-meter resolution. And we analyzed the importance of these different band combinations. So the left column shows the overall error, and then the other columns are the error per 10-meter height intervals. And it turns out that the RGB-N, so the RGB and the near-infrared sensor, which have 10-meter resolution, are the most important ones. They can actually work almost on par when we use all the bands as an input. Then the second ablation study that we run was to understand the importance of texture features that can be learned with a convolutional neural network. So a standard CNN would today learn something like 3x3 filter kernels, such that you can learn texture features, so spatial features. And by simply replacing these filter kernels with a 1x1 kernel, we do not allow the CNN to learn texture features. So we can see how in the last row the performance drops actually quite substantially, and we see a significant drop in performance for very tall canopies. So there it's really crucial to learn texture features to do better predictions. Then we used the trained models to compute country-wide maps for Gabon, for instance. And one very interesting area is this region here, which is one of the tallest mangrove forests in the world. So the trees can go up to 60 meters in height. And it turns out that our model can even capture and predict these heights in a meaningful way, while available global maps at that time really struggled to capture, for instance, these very tall trees. Then we also run that for Switzerland, and we can somehow conclude that canopy height can be regressed from Sentinel-2, given that we have the reference data to learn from. And we can actually estimate canopy heights up to 50 meters. So this drastically improves some observed saturation effects from prior methods. And the textural features and the 10-meter bands are the most important ones. So after these experiments, we thought, okay, since Sentinel-2 is available on a global scale, this approach might eventually be useful for global canopy height mapping, but we are lacking the reference data to train such a meaningful model. And this brings me to the second chapter, which is about regressing canopy height from JEDI spaceborne LiDAR data. And this work was done in collaboration with John Armston and Ralph Tuia from the JEDI mission science team. And to show you and explain you quickly what JEDI is about, I want to show you this super cool animation. So JEDI does not have its own satellite. It is mounted on the International Space Station. And it's this refrigerator-sized instrument that shoots laser beams down to Earth. And it collects data along 8 parallel ground tracks, as you can see here. And each shot is 60 meters apart, and the tracks are 600 meters apart. And when such a laser beam hits the surface, energy gets reflected. And what we get as a result is such a vertical profile, energy profile. So you see at the top of the canopy, we get the first return, and then at the ground, we get the last return. So JEDI is explicitly designed to measure forest structure and collects this sparse data with a 25-meter footprint on the ground. But the challenges are still that the data is full of unknown effects and is rather noisy because it comes from space. So we investigated here in this project how deep learning could actually help to support the calibration of the NASA JEDI space mission and how we could eventually model the uncertainty in these estimates. Here on the left, you see one of these waveforms that we get from the JEDI sensor. And as I explained already, the signal starts at the canopy top and then ends at the ground somewhere, but you can see it's rather noisy. And what we would like to estimate is actually the canopy top height, so the difference between the two. And the crucial aspect to model the uncertainty in these estimates is to turn a simple point estimate from a regression into a distribution over the output. And we do this by designing a convolutional neural network for a one-dimensional input signal that has 2 outputs, so one mean and one variance. And with this, we can approximate this conditional distribution when we estimate the canopy height given an input waveform. And we train this model by minimizing the Gaussian negative log likelihood, which, as you can see before, has the squared error in this loss function, but also estimates the variance over the output. And then on top of that, we do not only train a single model, but we train an ensemble of CNNs, each trained separately from scratch, from different random initializations, to get a diverse set of models. And then we can use the multiple outputs from these models, combine them, and get our final estimate, as well as the final variance, the uncertainty estimate, which models 2 sources of uncertainty. First of all, the so-called epistemic or model uncertainty, which models the lack of knowledge, let's say the lack of supervision data. So this source of uncertainty could be trained away by collecting more and better data. And the second source is the aleatoric or so-called data uncertainty, which is inherently in the data. So this part cannot be trained away by collecting more training data. To train these models, we still rely on reference data, and this time again from airborne laser scanning, and the JEDI Science Mission has provided us with this global reference data set where about 70,000 on-orbit waveforms were matched with airborne laser scanning data. And to do this, they first simulated the waveform from airborne laser scanning data and then computed the relative height metric such that we get a proxy for the canopy top height, which will then be our target when we train the models. So here are some results. On the left, you see the predicted canopy height against the ground truth, so the reference height from airborne laser scanning. And this resulted in a root mean square of 2.7 meters with a rather low bias. And on the right side, you see the root mean square error, how it performs when we start to filter out uncertain estimates. So here I highlighted the result when we removed 30% the most uncertain estimates, and you can see how the overall error can be reduced down to 2.7 meters at this point. So that's great. The predictive uncertainty is actually useful to identify erroneous predictions and then reduce the overall error. Here you see a map when we deploy this trained model on the first 4 months of the mission. And to actually visualize a global map like this, we had to pool this sparse data at a very low resolution to get a dense map. Otherwise, we would have a very sparse map and we would not see the patterns here. But the very good news is that now we have access to globally distributed reference data, and we can actually revisit the first part and think about how can we do this at a global scale to come up with a high resolution canopy height model for the entire land surface. So the idea is simply to combine Sentinel-2 data and the JEDI LiDAR canopy height estimates to produce a dense canopy height map with a 10-meter ground sampling distance. And this is the approach how we tackle this. Again, we use now a 2-dimensional convolution neural network to model canopy height from Sentinel-2 images, but we also adapt the uncertainty estimation approach for the image interpretation model. So we have 2 outputs, one's the mean and the variance. And then here on the right side, you see the supervision signal that we get from the JEDI footprints, and we get this sparse supervision signal. On top of that, we, as you can see here, illustrated on the left, we also include the geographical coordinates such that the model can actually learn some priors about regions in the world. Then at inference time, again, we use an ensembling approach and process multiple images from different dates to get full coverage in the end, because sometimes some regions might be covered by clouds, and there we cannot make a meaningful prediction. But by using about 10 images per location, we can obtain rather good coverage. And then we aggregate the predictions from the individual images to get our final map. Here are some details about the reference data that we collected. So we used 600 million JEDI shots with canopy top height estimates for the year 2019 and 2020. And then we combined that with about 13,000 Sentinel-2 tiles to create this global training data set. And to validate the model, we hold out about 20% of the Sentinel-2 tiles. So we hold out 100 by 100 kilometer regions to avoid some over-optimistic results due to spatial autocorrelation. So here I will present a few different strategies that we investigated to understand better how this approach works. So the graph on the left is a residual analysis, where negative residual means that the model underestimates the cheddar reference data. And we can see that from left to the right, the model underestimates the taller the reference canopy height is. So this result here is when we only use Sentinel-2 images as an input. And when we start to add geographical coordinates as additional inputs, we slightly improve this underestimation bias for the tall canopies. And then we also investigated a fine-tuning approach where we reweight the training data, because there is a long tail in the distribution of canopy top heights. So tall canopies are rather underrepresented. And then ultimately, we use this ensembling approach, which also improves the underestimation problem. And we achieve this final root mean square error of 6 meters and get this overall overestimation bias of 1.3 meters, which is sort of the price we pay to improve the performance for the very tall canopies. And why are we actually interested in improving the error on the tall canopies? It's because there we have the highest carbon stock potential. So it's very important to have low error on the tall canopies. Finally, we run this model at the global scale. So we had to process about 160 terabytes of Sentinel-2 image data to produce this global map. And here in the bottom, you see rezooms from interesting patterns that come up. So on the left, when I saw this the first time, I thought, oh yeah, there's like some artifacts in the predictions, but it turns out that that is actually a harvesting pattern in the US. And it's not a problem of the model or the data. And then we can also visualize the predictive uncertainty for every pixel, which combines this epistemic and aleatoric uncertainty. And when we look at the regions, so here these red lines indicate the boundary of the cheddar coverage data. So cheddar only goes up to 51 degrees north and south. So it never sees any northern parts. And we see that some regions actually have higher uncertainties than others, like for instance, Alaska, or then in Tibet, we see increased uncertainty. Okay, so to finish, I would like to show some potential applications now that we have these tools at hand. And one obvious application would be to use this canopy height data to map biomass and carbon stock. So here, this is from another paper that we were working on, where we used local carbon density data to calibrate a small model on top of it that then estimates above ground carbon density from the canopy height as an input. And turns out that the estimated canopy height from Sentinel-2 correlates very well with the above ground carbon density, even though for higher canopy heights, we see that the spread grows quite significantly. So there is some ambiguity in this relationship. And the second potential application is change analysis. So we can use the model and produce annual maps here for a region in California, where we produced the map for 2019 and another one for 2021. And then we can have a look at the difference between the two maps. And it turns out that this can be very useful to map the burned area from wildfires. So here in black, you see the outline from the agency that mapped the extent of this August complex, one of the biggest wildfires in 2020 in California. And the changes correlate very well with this region. Before I come to the conclusions, there are also some limitations in the current work, especially when we use JEDI data to train this global model. So when we look at the image below, on the left, you see the Sentinel-2 image, and then on the right side, you see the canopy height predictions when we train on global sparse JEDI reference data. And in the center, this is also some estimated canopy height, but the model was trained on local high-resolution reference data. And we see there's quite some difference in the maps. So the one in the middle can actually preserve a lot of spatial details, where the one from JEDI is much smoother. And there are several reasons why this happens. So first of all, the reference signal that we get from the JEDI footprints is the maximum height within a 25-meter footprint on the ground. So this is illustrated in the top right. So what we estimate actually is the maximum canopy height within a 25-meter footprint at every 10 by 10 meter pixel. And then the model only gets this sparse supervision, so it never sees the high frequency neighborhood information as if we would train from dense airborne LiDAR data. And then finally, there are some geolocation uncertainties in the version 1 JEDI data. So this has been improved in the next generation of JEDI data, but this geolocation uncertainty also leads to a blurring effect. So I think this is an interesting future direction to think about how can we preserve the small structures that are actually visible in the input image in our predicted map, even though we only have sparse supervision signal at hand. So to conclude, the take-home messages are that Sentinel-2 images are actually useful to map canopy height. Of course, never at the quality that we could get from an airborne LiDAR campaign, but it's much cheaper and scales to the entire Earth. And deep learning is actually key to extract predictive features. And when we use these approaches to model uncertainty, we can actually indicate potential errors, which is quite important to inform downstream applications about the errors in the map. So is it all solved? No, there are still open research questions, and I listed some of them here. So I already talked about the spatial resolution when we train on sparse supervision. But the question is also, how can we reduce ambiguity and the saturation effect in the predictions? And that, I think, by only using optical images as an input, there are some limits, so we should think about adding more data that can help to resolve these ambiguities, like climate data and so on. And then, of course, we would like to improve the geographic and temporal generalization. So if we would like to use this model to produce a new annual map within the next 10 years, and there might be some shifts in the data, predictions can actually go off. So we should be very careful in doing this. And then, of course, we already heard the keywords self-supervised learning and so on. It would be interesting to figure out if that can actually reduce the amount of needed training data for specific regions. And then there are some exciting future directions, like temporal analysis, as we have seen an example, and biomass carbon stock estimation, and then ultimately, quantifying how much CO2 is released from deforestation. And then there are also applications in biodiversity modeling. So these canopy height or forest structure maps can help to characterize habitat and can actually be studied if these are predictive input data to model biodiversity variables. So if you would like to read more about this work, you can go to my personal website or the group website, and you find all the links to the papers. And also, if you would like to explore the global canopy height map, there's a demo. Yeah. So with this, thank you very much for your attention, and I'm happy to answer some questions.
Thanks so much, Nico. There are plenty of questions, so we don't need a warm-up here. So maybe we can jump directly to the chat. There are some technical questions, some more, let's say, speculative questions. We can go by order. There are questions, for example, by Shine, that is arguing about, okay, you can estimate forest trees heights, but maybe, you know, having into account like the forest types or the density, right? I can give you like more, or the diameter. That could be also useful for, you know, for other monitoring purposes, right? Or the carbon stock, as you already mentioned. And that was like curiosity about if this is actually possible to correlate this kind of measures with health status of trees.
Yeah, so it's an interesting question. In the end, these modeling approaches are very generic and very flexible. So it all falls with the availability of reference data to learn these relationships. So if there is, if there's reference data available to train the models, then they are useful. But so far, they are trained for canopy height estimation, and but definitely.
Good. There is another kind of a technical question as well from Sylvia Zulfi. He says, what is the lowest height of vegetation that the system can actually detect? I think that you already mentioned the errors, yes, but
yeah. So in the graphs that I showed, we saw that there are some slight overestimation of low canopy height. Mm-hmm. I cannot really answer the question with a single number. But yeah, that's definitely something that might need a bit further investigation. But what we saw actually, when we, for instance, use the estimated uncertainty and start to filter out the most uncertain samples, we see that this overestimation bias of heights below 5 meters vanishes. So it goes down to 0. So the model somehow knows that in this low vegetation regime, there are some uncertainties, and it actually estimates a meaningful uncertainty there.
I actually had a question regarding that exercise, because probably I didn't get it quite well, but you were actually masking like the more uncertain predictions, let's say, right? Mm-hmm. On the basis of what? Because in the end, the uncertainty that the deep learning architecture can estimate probably will tell you something about the extrapolation, but not anomalies in principle, right?
Yeah, not sure if I completely understand the question, but what we use is the relative. So we normalize the estimated standard deviation with the estimated mean, and then there is some rules that we tuned actually to make sure that when we start to filter out uncertain estimates, that we preserve the full range of heights, because mm-hmm. you can also see that the uncertainties correlate and grow for the vegetation.
Okay.
When you just remove the highest uncertain estimates in terms of absolute standard deviation, you remove a lot of the high canopy height estimates, which is not really what you want.
Yes. Now I see. Yeah. Let's move back to the chat. There's like a couple of questions by Simon Lesnard. He says, the first one, what is the actual added value of using images contaminated by clouds? Why not filter them out and then only use the best possible, let's say the cleanest images? Or are you actually doing this? So
I would say we are doing this. Maybe I wasn't too clear in the explanation. What we do is we query the 10 images with the lowest cloud cover at the Sentinel-2 tile level. So the cloud cover that is provided with a 100 by 100 kilometer region.
Mm-hmm.
And we then hope that they will complement each other so that the cloudy regions in the best image are actually then visible in the next images.
Okay.
So the cloud region is actually removed before we do the aggregation using the cloud mask that is provided by the Sentinel-2 product.
Okay. Yeah, and the second question from Simon, it says, for the change detection analysis, you basically need to do this space for time substitution because the model does not learn the temporal dynamics from the JEDI data. Would it make sense to you to include ISAT2 data to let the model learn the temporal dynamics and then retrain on JEDI, or kind of, it looks like more an idea for transfer learning, something like that, or maybe fusion of different sensor data. It says, might help to overcome these limitations of space by time substitution.
Yeah, I mean, I should maybe add here that the model works on a single image only. So it has not learned any temporal features.
Yes.
So we do prediction for every individual date. And the main reason why we do it for multiple dates is to get full coverage. So that's why so far we just present annual maps by aggregating multiple images for that year. But you could, for every Sentinel-2 image that you get in the time series, you could predict a new canopy height map, which is just incomplete because some regions are covered by clouds.
Yes, yes. See.
And regarding ISAT2, definitely it would be a good idea to combine JEDI and ISAT, because ISAT actually goes over the poles and can fill in the gaps from JEDI. So that would definitely help to improve performance in the northern part.
Mm-hmm.
That's definitely a good idea. But of course, one has to be careful to harmonize ISAT2 canopy height data and JEDI canopy height data. This is something it's not too trivial, I would say.
Yeah, and I guess that you are also inheriting your errors, right, in the estimation of every snapshot, right, when you do the subtraction. So you can be, actually detecting the changes for wrong reasons, right, because of composition of errors or things like that.
Yeah.
Yeah. Yeah, I think that we have a question by Marcus Reichstein. He's around. Marcus, can you shoot?
Yes. Yeah. First of all, thanks both to both of you for this really nice talks. Now I have a relatively detailed question, maybe. So basically, you clearly showed that the texture is really important feature in the Sentinel-2 to predict the vegetation height. And I was wondering, on the one hand, do you have a kind of mechanistic of physical interpretation what this really is, kind of, or is it interpretable? Because it's really interesting, or if it's just the overall shape and then it infers something about the forest in general. And then the second question actually related. I mean, usually Sentinel-1 is very good for texture information. So did you think about using Sentinel-1, or is there any directions in this direction?
Yeah, thanks for those questions. So I'm always very careful in interpreting the learned features too much, right? We actually spend some time looking at the learned features, visualizing what they activate on, and you see like the simple features where they detect edges or specific colors and so on. This is something we can understand to some level, but then the more abstract features are not so trivial, especially because Sentinel-2 is a 10-meter resolution image. So for us humans, we really have to zoom out to see some structure. When we zoom in, we just see pixels, and we cannot really understand the textures there. Of course, one could somehow hypothesize that the model learns to detect shadows in some cases and so on, which might be the case in very highly structured forest areas, but not sure if that, for instance, is the case in the tropics when you have just very tall vegetation for a large region, you would not get these shadows casted by the sunlight, for instance. So the answer is that we don't really know what features they learn. There's no explainability built into this yet. And then the second question was about, what was it?
Sentinel-1 or, yeah, in general.
Yeah, Sentinel-1, exactly. So actually a colleague of mine, Alex Becker, investigated the combination of Sentinel-2 and Sentinel-1 for forest structure prediction. But so Sentinel-1 helped or improved the performance slightly, but not as much as we would have expected maybe. And one explanation could be that Sentinel-1 is actually a rather short wavelength that can only penetrate the top of the canopy. So it gives you some information about the surface, but it will definitely not penetrate deeper into the canopy and tell you something about the forest structure. So that could be one reason. And but of course, it could help in regions where we have frequent cloud cover, right? Because it's not limited to cloud coverage.
Cool. Yeah, thanks. Yeah, that's what I was thinking also.
Thanks. Let's move to another question. This time is Alistair Phoenix. He's asking, first, thank you for sharing this important work. The question is, due to the enormity of the data involved, are there plans or funding to continue rerunning and storing the output from this model, maybe annually? Lastly, is this data publicly available? If so, where can it be found?
So yes, it's first of all, it is publicly available, the global canopy height map. And we will also publish all the source code and trained models once this final paper is published. So everybody could actually take the model and rerun it. You would actually have to reach out to my former supervisor, Jan-Dirk Wegner, for the current plans. I'm not updated with the latest information, but it would be really interesting to run this model globally for multiple years.
Yes.
But before we do that, we should definitely spend more time in analyzing if the model already generalizes to different years. How well does it generalize, or are there systematic effects that we observe before we make large-scale computation and interpret the data? So if you go to my personal website, or if you search for the EcoVision Lab, you will find pointers to the data. If you Google for global canopy height and my name, Nicolas, you should find it.
Fantastic. I think this is more, I mean, this is brilliant, actually. This is more than necessary to advance science. I have like a couple questions, right? One of those that we have been working a lot on uncertainty estimation, quantification, and propagation, and this is kind of linked to the further use of these products into Earth system models, for example, right? And I don't know, for example, how I mean, honestly, how much do you trust the uncertainties that you or a deep learning algorithm can actually deploy, and if these uncertainties are well calibrated or not, or did you try out like different methodologies to see or to quantify the calibration level, and and if you actually trust that for propagating uncertainties in models?
Yeah, it's a good question. So there are two things that two strategies that we use to analyze the quality of these uncertainty estimates. So one is, as you mentioned, looking at the calibration of the uncertainties. Mm-hmm. So what that means is that we would like the uncertainty estimate to reflect the empirical error that we make in expectation, right? So the best we can do there is to hold out some validation data and then compare the empirical error that we make on the validation data and compare it to the estimated uncertainty of the model. And this looks rather well. So I do trust them to some extent. So the second approach that we investigated is to, as I described, this filtering approach, right? To see if when we remove the most uncertain data or estimates, can we actually remove reduce the overall error? So these two strategies, what we used to.
Mm-hmm.
Okay, thanks for joining.
That's really, yeah, and it is step actually when you deploy uncertainty estimates, because in the end, people want to know and people want to use them. I have a related question because I see we don't have further questions here in the chat. You have been working a lot on samples, right? For this these uncertainty estimates. But I was a bit curious about, did you try any other method, more like, I don't know, MC dropout or even bootstrapping, like so they have demonstrated like being efficient and easy and easy to deploy, right?
We had a look at MC dropout, for instance. We couldn't make it work as well as the ensembling approach.
Mm-hmm.
But I have to say that we relied mainly on the literature, which did this intensive analysis already for some computer vision applications. And so far, the literature somehow suggests that ensembles are still the way to go today. I'm not sure if you agree, but that's my.
I guess it will depend a lot on the data characteristics, the problem, and many other things. Yeah.
And then there's the fact that at the global scale, it's not so easy to, for instance, run hundreds of experiments and tune your hyperparameters and try different methods and so on. It's very computationally expensive. So one needs to do this at a smaller scale, and then somehow trust that the findings that you have at a smaller scale will generalize to the large scale application.
So thank you very much for your very clear presentation. Excellent science out there, and and your answers. I think that we don't have any further questions here in the chat. We have had like a great pleasure to have you both here, and I think that with great discussions and around this important and timely projects and problems that you are tackling. Thanks so much, both Devis and Nico, for presenting and answering all these questions. Now it's, I think, time for closing the session. Thanks for this discussion. It has been really fruitful, I think, in my view. Also, I would like to thank the attendees. Thanks for staying with us so late in some parts of the world, so early in the others. And remember that you can still continue the conversations in the neural network area if you're actually registered there. This is actually a very good opportunity to follow up with more technical questions, maybe some curiosities, and to interact with our speakers today. Our next talk in this seminar series, AI for Earth and Sustainability Science, will be on May 24th. And we will have an exciting talk entitled Physics Informed Machine Learning to Push the Ocean Frontier in Climate. And this time will be my colleague here in Valencia, Maria Piles, that will be the moderator. And if you want to know more about Earth and climate and AI, just sign up in our sister seminar series, AI and Climate Science, convened by Duncan Watson-Perez and Philip Steer. So thanks, everyone, and have a good day.
Thanks for organizing, and thanks for attending. Bye-bye.
See you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, Like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
AI is a powerful tool.
This summit can help ensure that artificial intelligence charts a course that benefits humanity and bolsters our shared values.